Hello, can you hear me?
Yes.
All right, so now we were in. Now we have these two lectures. I don't know how I'm going to finish this. I don't know. Maybe I'll try to see how much I can go tomorrow. Otherwise, I will try to organize one more lecture next week. Sometime next week. I think now we can also do it in the morning because yeah. I mean, I think now the people who are the time zone is not very problematic. So we could do it in the morning. So I will check with Patricia when this room is available and let you know. If there is a need for one more lecture, which I think we will need. Okay. So we arrived up to so we did the 12.3. We did the 12.3, the theorem 12.3, and also we did theorem 12.4 also. Right? Yeah. So there, I mean, you see that just from the fact that this Cartesian form is non-degenerate, we can get so much information. So I mean, at the end, now up to this point, what we have learned is that the Lie algebra structure is, of course, the Cartan generators, they commute with each other. So HIs are in the Cartan subalgebra. So I think what we were calling capital H, right? Yeah, capital H, Cartan subalgebra. That was that. And then HI with the X alpha was equal to alpha HI X alpha. So these were the non-zero roots, and alpha was the non-zero roots. So alpha belongs to delta. Delta is a set of roots. So this is the set of roots. And H is again in the Cartan. And finally, X alpha with X beta, also we learned that, so this is equal to n, some number, which we don't know what number is, this is some number, X alpha plus beta. Okay. If alpha plus beta belongs to delta. So there are several possibilities here. Or if alpha plus beta equal to 0, which means beta is equal to minus alpha, so X alpha, X minus alpha, in that case we saw that it was B of X alpha, X minus alpha times H alpha. And we also know that this is not 0. We also know that this quantity is not 0. This was, I think, one of the theorems. Yeah, it's did we prove that the statement was? So for the 12.4. Okay, and then finally, if the third possibility is that alpha plus beta is not in delta. In that case, of course, this is 0. So this was that. So we learned all this, and also we learned that the dimensions. I think this was one of the statements we proved. The dimension of G alpha So dimension of G alpha. So this is the subspace which they all had the same root, alpha. Right? This is always one dimension. And also we had we had also the statement that if alpha is a root, if alpha belongs to delta, then then n alpha belongs to delta only for n is an integer, only for n equal to 0 or plus minus 1. Well, 0 means it's a karma, no? So forget the 0, but plus minus 1. So just x alpha and x minus alpha. You don't have 2 alpha or 3 alpha and so on and so forth. So this was the main things for what we did. Now let's go on to the next point. And in doing so, we have used many times the SU2 algebra structure. No? In many of these proofs, arriving up to this point, we consider this what we call alpha strings. Alpha string. So this is a definition now. I mean, we just give a definition. So we say alpha string. So alpha and beta belong to delta. Then we call alpha string through beta. Through beta is a set of all the roots, which is beta plus n alpha. So this is the set of all roots where n belongs to integers. We use it already in one of the proofs. I think the second or the last theorem. We considered this string beta plus n alpha. What is the meaning of this? Because this will provide a representation for the SU2 subalgebra, which is spanned by x alpha. So what does it mean with this thing? Is basically it gives a representation for the SU2 subalgebra. Generated by x alpha, x minus alpha, and h alpha. No? So this gives a, because in this, when you apply this x alpha on any of these states, n goes to n plus 1, right? When you apply x minus alpha, n goes to n minus 1, and when you apply h alpha, it stays there itself, right? So this gives a representation. Need not be reducible representation, but okay, some representation. So far. Now there is another theorem. We try to look at that. Theorem 12.5. Theorem 12.5. So the first statement is, so we have again alpha, beta belong to delta, the roots. And so consider an alpha string. So take an alpha string through beta, and suppose the string, string can be something like beta. Let's say beta is here, beta plus alpha. I'm just plotting it. Beta plus alpha, beta plus 2 alpha, beta minus alpha, beta minus 2 alpha, and so on and so forth. But so these are all consecutive, no? These are all consecutive points. So in other words, x minus alpha will take you there, x plus alpha will take you there, and so on and so forth, right? But it could be that it ends somewhere. Let me just call it, so it goes there, say up to this point, beta plus p alpha. Let me see. The symbol is what? Beta plus q alpha in this notation. Beta plus q alpha. It goes up to beta plus q alpha. Not more than that. Meaning the next one, beta plus q plus 1 alpha, is not a root. This is not a root. So it stops there. I mean, in any case, it has to stop somewhere, right? I mean, we are not talking about, we are talking about finite dimensional algebras. So it cannot continue. And same thing here, it goes up to, say, beta minus p alpha, and nothing further. Here it is, I mean, if you apply further x minus alpha, it's not there. So this is not a root. So beta minus p plus 1 alpha is not a root. Is not a root. So it stops here. So this is an unbroken string. Okay. Of course, it could happen, perhaps. I mean, a priori we cannot say that, right? It might happen that maybe this one is missing, but beta plus q plus 2 alpha is a root, no? I mean, at the moment we cannot exclude it. Although one knows it cannot be, right? Because, I mean, given the knowledge that we have about SU2, I mean, if I have a q plus 2 alpha here, beta plus q plus 2 alpha, then think of this as a spin j. Then, you know, j minus 1 should exist, j minus 2 should exist, no? So, but still, at the moment, let me just take this. So we take this chain, the string, so this is unbroken string. So everything exists in between. Unbroken string, which ends on the both sides, which ends on both sides. In other words, the next one is missing, and also the previous one is missing. So then that's it. So then the statement is, so the first part of the theorem is, the first part of it is 2b of h alpha, h beta, divided by b h alpha is equal to p minus q. So that's the first statement. So you see this, I mean, if you can prove that, this is quite interesting, because it says that the ratio of this Cartan-Killing forms, this ratio, is just an integer. Okay, p and q are both integers, right? It's an integer. In particular, it means also they are real numbers. Because so far we have not said anything about, we have complexified everything, right? So in principle, it could be complex numbers. But in fact, not only it's real, but actually these are integers. Again, it's not surprising. I mean, okay, we'll see that. Okay, so how do we prove that? So the same thing, because this is going to be a representation of the SU2. The SU2 subalgebra, which is denoted by x alpha, x minus alpha, and h alpha. This SU2 subalgebra. With respect to that, this is a representation, because x alpha acting on that would have taken you here. But that is missing, that root is missing. So x alpha acting on this should be 0. So it's the highest weight state of this representation. Similarly, x minus alpha acting on this would have taken you there, but this root is missing. So also x minus alpha annihilates it. So it's the lowest weight state. And then x minus alpha will take you successively, step by step here, and x plus alpha will take you successively there. H alpha keeps you there in the same space. Right? So this is a representation. So then I can again do the same trick that we keep doing, the trace of h alpha, which can be written as some number. This number is 1 over b x alpha x minus alpha. Okay, but it's some number. I don't care about this particular number of trace of the commutator of x alpha x minus alpha. I mean, everything is add. I forget to write add, but I mean, we are just entirely talking about the adjoint representation everywhere. Okay. So this is what it is, and then, but the trace of a commutator is 0. Okay. So we know that this has to be 0. So this will always be the case when you're looking at a genuine representation. This will always be the case. As we saw in SU2 case, right? I mean, when we studied SU2, trace of J3 is always 0 in any representation. Precisely for that reason. Okay. So now we can calculate directly what it is. So it's going to be, so beta plus n alpha, okay, sum. Okay, let me just, not to keep track of the minus and plus signs, let me just call minus P is equal to R, okay, and Q is S. So Q is S. So that I don't have to keep putting the minus signs. At the end, we can put the R equal to minus P. So I want to sum from R to S. Okay. So this sum, that's what it is going to be, right? Because H alpha is diagonal in all of these spaces. In a given space, say for example here, it is going to give me beta minus P alpha of H alpha. And so on. So in each one of them, it will be this acting on H alpha, this acting on H alpha. So it's going to be the sum. And we already know the dimensions of each of these spaces is 1. Right? I mean, if we didn't know about the dimension, it would have been dimension of the space, this G of beta plus n alpha. But we know this dimension is 1. Right? That was one of the things that we proved in the last theorem. The dimensions of each of these spaces is 1. So therefore, this is just one dimension, so is this. So then we can sum it up. So we get here beta of H alpha times how many terms? This, this term is independent of n. So when I sum over n, so this is n equal to R to S. So this is going to be S minus R plus 1. Right? That many terms will be there. S minus R plus 1. Okay. Okay. Plus this term, n. So now what it is, alpha H alpha, this is independent of n. But now I have to sum n from R to S. Okay. That is going to be S minus R plus 1 times S plus R divided by 2. That's the usual, the sum over n. Right? You all agree with that, right? So therefore, we are saying that, but this whole thing is equal to 0. So we are saying, well, S minus R plus 1 is a common factor. So you get here S minus R plus 1. Okay. This is certainly not 0. And then inside you have B beta of H alpha. Beta of H alpha is the same as B H alpha H beta. Okay. And then you have here plus S plus R over 2. Alpha H alpha, which is the same as B of H alpha H alpha. So we arrive at this important conclusion that 2 times B H alpha H beta divided by B H alpha is equal to minus S plus R. That's good. Okay. Now the one important thing to notice here is that this has no, on the left hand side does not know anything about S and R. This is simply alpha and beta. Okay. So, so therefore now suppose, so first of all let's say that there is only one unbroken chain. We want to show first of all that there's only one unbroken chain. We said, okay, this is an unbroken chain, but who knows, maybe there is another chain starting from another point here, and there is another chain out there. Or maybe there is another chain here. That in principle it could be possible, although we know that cannot happen from the SU2, knowledge of SU2. But let's just see how this works out. Yeah? So now suppose that there is another chain which starts from R prime to S prime. Okay. So suppose, so this is the conclusion, right? At this point you have just arbitrary S and R. Huh? The only condition is that at the R, this is annihilated by X minus alpha. So the previous one it does not exist. And the S is something such that it is annihilated by X plus alpha. So the next point is missing also. The next root does not exist. Okay, so here Now suppose there is another chain which starts from R prime up to S prime, okay? Where R prime and S prime may be different from R and S. Again, unbroken chain. In that case, we would also find that this should be equal to minus of S prime plus R prime, right? So suppose there is another chain. So there is another chain, another unbroken chain, which starts from alpha plus R prime, beta plus R prime alpha, and goes all the way to beta plus S prime alpha. So if that happens, then again I can apply the same logic, because this will again be a representation. So trace of H alpha should vanish here again. So we will find that this is the answer. Right? But now look at this here. I mean, if, so let me erase this part here. Okay. So if, suppose the S prime, if S prime is equal to S, then there's nothing to, then we are talking about the same chain, right? If S prime equal to S, then this, if S prime equal to S, then it tells also that R prime is equal to R. Then we are talking about the same chain. Our question is whether a different chain is possible. So let's suppose S prime is greater than S, or S is greater than, argument is the same. Suppose S prime is greater than S. Then, so what are we saying? We are saying S plus R equal to S prime plus R prime, right? From that equation. So if S prime is greater than S, then clearly for this equation to be true, to hold, then R prime must be less than R. Right? So the picture is that we have a chain starts from the R to S, but then we are saying there is a chain which starts from R prime to S prime. Because we said if S prime is greater than S, so S prime is greater than S, so this is the positive direction, let's say, this is greater than S, then R prime has to be less than R. So that means we are saying that now there is an unbroken chain starting from here to there, right? But we also said that there is an unbroken chain from here to there, but the previous one was missing, this was not there, and this was not there. That's not possible, right?
Professor?
Yeah.
One question. We denoted that R was negative.
Can you speak a bit louder, because I can't hear very well. I think the volume is too low.
We said that R was negative. If R was negative and we have R prime minus less than R, it means that we have to not move to the left, or we have to move to the right in that case that you draw, or not.
No, I mean, so I mean, we said that, I mean, this has to, let's assume S prime is greater than S, which means S prime is, if this is the positive direction, then S prime is somewhere here, right? Now, but this equation has to be true. S plus R equal to S prime plus R prime. If this is greater than that, then this must be smaller than that, right? So therefore R prime is less than R, no? So it's in this side. Is that clear?
Yeah, I think.
Yeah. Okay. So that's a contradiction, because then if this was the case, then what we said previously was not correct, because we said this is an unbroken chain with the one previous and the one next one is missing. That cannot be, because you know. So therefore, the only conclusion is that S prime is equal to S, and then therefore R prime is equal to R. Right? Because I mean, you could also consider other cases where S prime is less than S, but then R prime will become greater than R. So the S prime and R prime will sit here. Then again we have a contradiction. So the only possibility is that. So this means that there is only one unbroken chain. That's it. Nothing else outside it. But since we know that we already said that beta belongs to the beta is inside this chain, because that was our starting point. We said beta exists. No? Beta exists inside. So therefore, we definitely conclude that R must be negative, right? R must be negative or 0, but cannot be positive. Okay, that is why we said that, okay, this goes up to beta minus P alpha, and that goes up to beta plus Q alpha. So basically we are saying S is some minus P and R is Q. Oh no, other way around, I think, sorry. Yeah, S is the bigger number, right? And R is that. Yeah, we are taking S to be the bigger number. Okay. So that is clear, right? P is non-negative, non-positive. It could be 0, of course, right? That means the change starts from beta to beta plus. That could happen. But not positive. This will not be positive, positive number. Because I know beta exists. That was my starting point, that I assume that beta is a root. So beta exists. Huh? So that's the structure. Okay. Then, the next point, is it okay? Okay, the second statement is that beta equal to C alpha, where C belongs to complex number, any complex number. So consider such a situation. So I know alpha, so I'm taking alpha belongs to delta. I know that alpha is belong to delta. Now my question is the following. Is it possible to have another root, call it beta, which is C times alpha, where C is any complex number? Okay. Is it possible that such this is a root? So question is, can C alpha or can beta, does it belong to delta? So this is a question here. Huh? So we want to ask that. We already know something else. We know that at least if C was an integer, right? We already proven in the previous theorem, if C was an integer, the only possible value would be 0 and plus minus 1. But now we are asking more general, not just integer, anything. The previous, remember that theorem, what was it? The previous theorem was in the third part of the 12.4, the statement was that Gn and alpha is empty except for n equal to 0 plus or minus 1. So, but now we are asking for more general. We are not just taking C to be integer, but C is arbitrary complex number. Okay? The complex number we are taking because we have complexified the Lie algebra, right? So everything could be complex in principle. Okay. So that is right reason. Okay, so the answer to that question is, so again, let's look at this formula 2 B H alpha H beta divided by B H alpha is equal to P minus Q, right? P minus Q. So this was the first part. But now specialized for the case where beta is equal to C alpha. Okay. So what will happen? H beta is C H alpha. Okay. So C is a number, so I can take it out. These two cancels. B H alpha cancels with denominator. So this equation implies that 2C is equal to P minus Q. So C is not complex number. I mean, C has to be some integer divided by 2. P minus Q is an integer, so it can be divided by 2. Now, what we are saying is C is equal to P minus Q by 2. Okay. Similarly, if you know, so this was the alpha string through beta, right? But you could have also considered beta string through alpha. Okay. In that case, the formula would be 2 times B H alpha H beta divided by B H beta is some integer. Is an integer. No, appropriate some another p tilde, q tilde, some value, but whatever it is going to be some integer. So we are considering now the other thing. So here we start with the alpha plus beta, alpha plus 2 beta. So this is the string, alpha minus beta, right? Because that is the point. I mean, you see, the reason why it becomes so intricate also, is that for every root there is an SU2 subalgebra. So for H alpha, for alpha there is a subalgebra, alpha minus x alpha, x minus alpha, H alpha, right? This forms an SU2 subalgebra. Similarly for beta, there will be another SU2 subalgebra, H beta, X beta, X minus beta, and H beta. So you can consider now the beta string through alpha, right? That will be the second SU, the beta, let me say, SU2 labeled by beta, that representation. So but again, we'll get the same equations, that this is going to be appropriate, suitable P, let's say the lowest one here is P prime, and the lowest one, highest one is Q prime, okay, minus P prime and Q prime. Then this is just going to be P prime minus Q prime, yeah? Which is an integer. But then this equation, if I substitute now beta equal to C alpha, then denominator you get C square, the numerator you get a C, right? So 2 over C is an integer. Okay. So the only possibilities are, so we have only possibilities are C equal to, so the possibilities from here are C equal to 0. So C equal to 0 plus minus half plus minus 1 and plus minus 2. Plus minus 2 we already know it doesn't exist, because if alpha is a root, then 2 alpha is not a root. This we know already exists. This is plus alpha, minus alpha, and that is H alpha, that's fine. But if this is the case, then you see the beta, so then alpha becomes equal to 2 beta. Right? If we substitute C is equal to 1/2, plus or minus half, then we are saying alpha becomes 2 beta. Okay? But that's again not possible, because if beta is a root, 2 beta is not a root. So this is also not possible. So the only possibility is C equal to 0 plus minus 1. Okay, that's good. Now, the last statement is, this was the point, right? Because this was the statement. We said that up to now we came to the conclusion that if alpha, so if you look at the commutator x alpha, x beta, I know whatever it is going to be x alpha plus beta, right? Times something, and alpha beta. But now the question is, could it be that somehow for some particular values of alpha and some particular roots alpha and beta, even though alpha plus beta exists, okay, maybe this coefficient is 0. No? That's a possibility. Because we don't know whether this coefficient is 0 or not 0. All we can say is that this commutator must have an eigenvalue alpha plus beta. Whatever appears on the right hand side. So it must be x alpha plus beta, right? If alpha plus beta does not exist, then I know this doesn't exist, so it's 0, right? But if alpha plus beta exists, so whatever it is going to be proportional to that, but that proportionality constant could be 0. No, that might have happened. So now the statement is that this cannot be. So if alpha plus beta belongs to the root, is in delta, then this n alpha beta cannot be equal to 0. Or in other words, x alpha x beta cannot be equal to 0. This cannot be. That's what we are saying. So how to prove that? Again, let's consider chain again. But now, take the chain. So suppose, so again, we assume the contrary. So I assume that this is 0. And then we come to some contradiction. So assume that this is 0. In that case, you see, I can take this string, alpha string through beta, which was, as we said, it was like beta minus p, I think we were calling p, yeah, p alpha, and the next one, and so on and so forth. Then you have a beta here, beta plus alpha, beta minus alpha, and all the way up to beta plus r alpha, beta plus q alpha. Right? This was the original string. But if this is true, then you see you could have considered a smaller space. You could have considered this space. Right? Because we are saying that if I apply x alpha on that, that is 0. So it doesn't go there. Right? If I make an assumption that this is 0, then I can consider even a smaller space. And that itself will be a representation of the SU2. Because x alpha annihilates it by this assumption. So then we will get, so then I can talk about the trace. Then I can do the trace over of H alpha in a smaller space. So where the sum, so this is over summed over n, where n starts from minus p up to 0 of g or g plus g of beta plus n alpha. Okay? This means that just sum over this part. Just take the trace over this space. Here, you see, I can again use the fact that, I mean, this H alpha is a commutator of x alpha with x minus alpha, but x alpha annihilates this part, so it stays, x minus alpha annihilates this already, that we already know. So this becomes a smaller space, which is again a representation of the SU2 subalgebra. So, but then we will find, so this is the same as taking q equal to 0 in that formula. So we'll find from this that 2, so from here we'll find the same equation as that, but now this q is replaced by by 0. So we'll have the equation 2b h alpha h beta divided by b h alpha is now simply equal to p. Because q is 0. It is right. I mean, that formula we got by taking the sum from minus p to q. Right? You know, right? I mean, we did from r to s, but r was minus p and s was q. That is what gave that formula. Okay. But if I take now the sum over from minus p to 0, which means q equal to 0, I mean, it's the same sum, you will just get that. Okay. But on the other hand, I know that q is certainly not 0, because here the discussion was only about what are the roots, right? Q is certainly not 0, q is at least 1. At least 1, right? Q is greater than or equal to 1, because we are saying that alpha plus beta is a root. Okay? So at least, so q is greater than or equal to 1. So this cannot be consistent, because we have a formula here and a formula here, but I know q is greater than or equal to 1. No? So this cannot be. So therefore, there's a contradiction here. This cannot be true. So this means, so this implies, so this contradicts. Since we know q is greater than or equal to 1. Because alpha plus beta plus alpha is a root. Because beta plus alpha belongs to the root. So our starting assumption was wrong. So this commutator is not 0. So this implies that the commutator x alpha, x beta is not equal to 0. So which means n alpha beta is not 0. Okay. So, is everything okay so far?
Good question, Professor. Why we allow C to be 0?
Why? What is to be 0?
C to be 0. It is that valid for the valid value for C.
Ah, no, C equal to 0 is the Cartan space.
Okay,
No,
because
C,
in this two relations, C equal to P minus Q over 2 and or 2C equal to integer. Is it possible for C to be 0 for a second relation that we found? 2 over C equal to integer.
I mean, C equal to 0 simply means H beta is, so C equal to 0 means beta equal to 0, right? But beta equal to 0 is just the Cartan generator. It's a Cartan space, right? So that is always there.
Okay, so from the beginning we know that.
Yeah. So the point here is that what are the possible things? So I mean, that would be, if I take beta equal to 0, then I mean, yeah. So beta equal to 0, then, no, but that, let me see. I mean, it's a beta equal to 0, just means the starting point, you start from the 0 point, right? This is 0. So then you'll get alpha, minus alpha, and so on and so forth. So, I mean, here the question is the following. What are the possible roots? The question is C alpha a possible root? No? And but we know C equal to 0 is of course a root, right? So yeah. I mean, in fact, what happens if I take C equal to 0, it just says P equal to Q, right? Yeah, the P equal to Q, because it will be equally distributed, you know. If you have a plus alpha, there's a minus alpha. Plus 2 alpha, if it was, you know, there will be minus 2 alpha. But of course, this is not there anyway, right? So that just says that if I take beta equal to 0, then the corresponding chain will have P equal to Q equal to 1. That's the idea. So yeah, so this will be possible if I take C equal to 0, that just means P equal to Q. P equal to Q. And actually, in this particular case, we know it should be, each of them should be equal to 1. Because we know already that if alpha is a root, 2 alpha is not a root. So in that case, it just P equal to Q equal to 1. Anything else? So now the last part of this chapter is, so far we discussed all this we complexified everything, right? But we'll see now that there is there is a kind of a real subspace of the Cartan subalgebra where the metric is possible. It not only is real, but it's really possible. Okay? Then we can think about geometrically, like the way we were drawing all these diagrams, you know, the alphas and betas and angles 120 degrees and so on. It was all we were drawing in a Euclidean plane, right? But right now we are all discussing, we are using complex algebras. But what we'll now see is that you can take a real subspace where the metric is possible. So the last point is that now if you take H alphas, I mean the reason is because we already have B, H alpha, H beta. So these are all integers. I mean, so you see that this ratio is integer. So certainly is real number, real, right? So what we do now is to take look at all the H alpha and consider the real subspace, which I call real subspace, HR. So the original Karta subalgebra space was complexified, right? But now I'm going to take a real subspace with that. And the real subspace is defined as simply real numbers times H alpha and some rho alpha. So any element which is obtained by taking these H alphas for all the roots, alphas are the roots, okay? So alphas are all the roots, okay? And multiply them only by real numbers, not complex numbers now. Then we are claiming that this is what we call HR, and what we want to prove is that on HR, the Kartan-Killing form is positive definite. Is positive definite. Okay, this is an important point here. It's positive definite. So that now we can, once we establish that, then we can start visualizing everything in a purely geometric contour. We can really draw pictures, alpha, betas, and so on a real Euclidean space. So what is the idea here? So first of all, we already know from this, if alpha, beta belong to the roots, that that same equation, 2b H alpha, H beta, divided by b H alpha, is some integer. Let me just call it n alpha beta. Okay. So it's a number which will depend on the length of the chains and so on, length of the alpha chain from the p and q, which will be determined. I mean, so it will depend on alpha beta. Note, one has to choose some convention. In general, n beta alpha is not the same as n alpha beta. Okay. This need not be. So one has to keep in order. One has to choose some order defining this. So we have used this definition, n alpha beta. The reason is that this n alpha beta is related to the alpha chain through beta, whereas n beta alpha is the beta chain through alpha. So they need not be the same. No? So we should distinguish between these two numbers. Okay. Now, so how does one prove that? The thing is that we also have another formula from one of the previous chapters, right? That B of H alpha, in general, B of H and K, two Kartan generators, was simply the summed over gamma H, gamma K, gamma over all the roots, right? This was one of the exercises which was our starting point, right? Many of these things we have deduced starting from this basic formula. This is nothing else but it's just a statement that H and K are diagonal, no? In this basis. If I look at this is the Karta, and here are the X alpha, the root spaces and so on. And when H, so a joint of H, add H, acting on that is simply going to be diagonal. It will be 0 here because it commutes with the H itself, and here it was alpha H. So here if I have X beta, then beta H, and so on, right? It was completely diagonal. These were the eigenvalues. So add H, acting on X alpha, is simply alpha H times X alpha. So add H in this basis is completely diagonal, right? And similarly add K. So this will be nothing else but the trace, this quantity is trace, add H, add K. Both are Kartan, so both are diagonal. And so this guy will have eigenvalue alpha H, this guy will have eigenvalue alpha K, and then we take the product, so it will become alpha H, alpha K, beta H, beta K, and so on and so forth, right? And then take the trace will give you this, that, where gamma is summed over all the roots. This was just the starting formula. So using this formula, then that is, you remember that, right? This was, I think, one of the earlier chapters. I'm not sure if it was this chapter or... It was an exercise actually. It was an exercise. Right? Yeah, 7. Okay. Yeah. So this was an exercise. I think you already done that. Okay. So using this now, so now specialize to the case. This is for arbitrary h and k, but now take both of them to be h alpha. So b h alpha is equal to gamma h alpha, sum over gamma. Okay. But what is gamma h alpha? Gamma h alpha is nothing else but b h alpha h gamma. Right? I mean, that was again going back to the older previous definitions. That is how that was what it was. So substituting that here, we see that b of h alpha is equal to b of h alpha h gamma square summed over gamma belonging to the roots. Okay. Now let us use this formula, but just put beta equal to gamma. So b h alpha h gamma is 1/2 of b h alpha alpha times n alpha gamma. Right? So I mean, this formula tells you, that formula tells you that b of, just substitute beta equal to gamma. So h alpha h gamma is equal to b h alpha divided by 2 times n alpha gamma. Okay, that formula. I just substitute, just take beta, instead of beta, I just take gamma. And now we substitute this here. So we substitute this expression here. Then we find that it's b h alpha equal to, so 1/2, there's a square here, so that makes it 1/4. And then b h alpha square, b h alpha square from there. And then sum over n alpha gamma square summed over gamma. I mean, these guys do not depend on gamma, so I took them out. Huh? So this is the formula we get. And now we already have proven one of the statements in one of the previous theorems that b h alpha is not 0. Right? Yeah, it was this. We already know that this quantity is not equal to 0 from the theorem 12.4, number 2. From BH alpha is not 0. Okay. So what I can do, I can remove one of them, right? So therefore, then what we find that BH alpha H alpha is 1 divided by all that. So this implies, from that, since BH alpha H alpha is not 0, that means I can divide it, no? The BH alpha alpha. So we find that BH alpha H alpha is equal to 4 divided by sum over n alpha gamma square. So now I can substitute that back here and get an expression for also B H alpha H beta. So B H alpha H beta is equal to 1/2 this times that, but then I substitute that here, so 1/2 cancels with that. So you get 2 divided by sum n alpha gamma. I should put the comma here to remember that, square times n alpha beta. So that's the four. No, I think I made a mistake. No, this was fine. BH alpha. Why is there a factor of 4 here? Strange. There's a mismatch here. I think there's a typo here. It should be 4 there in the, I mean, this expression. If you look at, there's a typo here. This should be 4. There in the notes it is 2 here, but it should be 4. But anyway, this things are not important actually. The important point is that both the BH alpha alpha and BH alpha H beta, so these are all rational numbers actually. This is in the what we call Q. Q is a rational number, so it's a rational number. Okay. And also this is a rational number. Q. So the reason why I went through this is because you see at the moment what we are saying, this relation tells you a ratio is some integer divided by 2. But we don't know individually what they are. It could be complex, who knows, right? Individually they may be complex, but the ratio may be always integer, or some integer divided by 2. But what we have now with this argument, what we have shown is that actually both numerator and denominator are rational numbers. Real, of course, and rational numbers. So that's the thing. So therefore now, if I look at now this space here, right? This means an arbitrary element of the space, let's say H, will be some combinations, let's say X alpha, H alpha, where X alphas are all real. Summed over alpha. Okay. So now if I take similarly H and H prime, if I take for example B H H prime, where H prime is again of this type, this is all going to be real because you just use the linearity properties. Then at the end of the day, it will involve a real number X alpha times X alpha times X beta times H alpha H beta, B of H alpha H beta. So this is all going to be real. So this means that the B, the Cartan-Killing form, restricted to this space is all real. There's nothing complex about it. Okay, that's one statement.
Professor, I have a question.
Yeah.
Here we have quadratic form for BH alpha alpha, and we may expect 2 values for. I didn't understand how.
No, but then you can cancel this, right? I mean, one of the factors cancel. This is the same.
Yes.
Yeah, so that's why I did that. I mean, yeah. So this is why this came in the denominator, and there's a factor of 4. Yeah. But the point was that it was crucial that, I mean, if this was 0, then this equation is an empty equation, right? So, but the fact that we had to use the fact that this is not 0, so that I can remove one factor from both sides. Okay. Finally, so this is and if you now look, this was so inner product between any 2 such elements, H and some H prime with X alpha prime. So if I take H prime again equal to some alpha X alpha prime, H alpha, then if I take the inner product of these 2, then using the linearity, you'll have terms like X alpha X beta prime, B of H alpha H beta. But we are saying B of H alpha H beta are all rational numbers. In particular, it means real numbers. And X alpha prime or beta prime are also real numbers, right? So B of H prime will be real numbers. Will be real number. And finally, if you look at the B of HH, the same H, that is, of course, nothing else but B that we already know is gamma H square summed over gamma belonging to the delta, right? This is again from that exercise. B of HH is nothing else but gamma H square. But gamma H itself is real because this is nothing else but B H gamma H, right? Now this thing. So this is the same as this square. Sum gamma belong to delta. Okay. Now H, if I expand it like this, is going to be X alpha, B of H gamma H alpha. But B of H gamma H alpha is again rational number. Okay. And X alpha is real. So this quantity is real. A real number square is always a positive number. I mean non-negative number, positive number, right? So this is positive. It's positive definite. Of course, for H equal to 0, I mean 0, just take 0 element, then of course it will be 0. So this is important. It's a positive definite. So we have obtained a positive definite space. Right? So in this space, this is what we call HR. In this space, the Cartan-Killing form is positive definite. So we can just use our standard notions, geometrical notions of Euclidean space. So that is the main point here. So I think this finishes this chapter because I'm not going to talk about now the uniqueness of Cartan-Killing form. But it's instructive. I mean, just take a look at it and see this 12.4, section 12.4. See if you understand them or not. Huh? Or if you have some questions, then we can discuss next time. Because I like to start cutting many topics. Otherwise, I will not get to the point. Okay. Now, chapter 13, I will come back to it later. So, chapter 13, what it does mainly is just to go back to the classical, the matrix algebras that we already studied. I mean, the SUNs, SONs, and SPNs, symplectic, right? These are the three matrix algebras that we have studied. So for all of them, so what it does is to just construct all the, take the suitable Cartan generators, construct all the roots, non-zero roots, and so on explicitly, right? So take a look at that. And if there's any question, maybe we can build this. If next week we have a class, then we can come back to that. Huh? But let me go now directly to chapter 14. So this was chapter 14. So chapter 14. Any question? But before that, any questions here now?
One question, Professor. Can we choose a basis of any vector space to be non-unit vector? Or it must be, if the basis has to be a unit vector?
No, can be any. Basis just means that any vector should be, you should be able to expand as linear combination to the basis. That's all. Doesn't matter at all. I mean, for convenience, you might want to choose not unit, right? But it's not necessary. Okay, so now let's go back to this. This is very important because now we'll be able to geometrically visualize it. Just like what we were doing for SU3, we were drawing these roots, right? Now we can think of that. We can think in that language. So it will be always in this space, HR, I mean the real space. And the corresponding dual space, H star. So you can again go to the dual space because that's where the roots live in the dual space. I mean, this metric gives you an isomorphism between the dual space and the original space. So we have this HR, and then H star R is again a real.
Does it give an automorphism in the dual vector space?
Yeah. Of course, that will happen only if the B is non-degenerate. But that we are assuming throughout that B is non-degenerate. Okay. Now, so let's now look at, so remember what was n alpha beta? N alpha beta, I mean, so this was 2 BH alpha, BH alpha, H beta, divided by BH alpha, H alpha. This is what we are calling n alpha beta, right? Okay. But this is the same. Remember that we could, using this Cartan killing, we could introduce directly a metric on the root, on the dual space, H star. But that was, this is nothing else but alpha beta. We were calling alpha beta, right? This one. So there's a factor of 2 there, and alpha alpha. So it's alpha dot beta, and there's alpha dot alpha in the usual way of thinking about the vector. Okay, and this we know is P minus Q. Okay, so this was the alpha chain. So we're looking at alpha chain through beta, and we had beta plus Q alpha, and it's coming beta minus P alpha. So this was the chain. Okay. Now, what can we say about, I mean, so suppose I compute n alpha beta, and let's suppose n alpha beta is positive. So suppose several possibilities. Suppose n alpha beta is positive. This is an integer, of course, so some positive integer. Okay. Then, if I look at this here, then that means P must be greater than Q, right? P must be greater than Q. So for sure, I know that at least P is 1, at least. I mean, if Q is 0, P is 1, right? So at least P is 1. Could be, of course, more, depending on the value of Q. But so this tells me that at least this implies, for sure, that beta minus alpha is a root. At minimum. I mean, this we see that the moment I see alpha beta is greater than 0, then it implies that beta minus alpha is a root. Could be more, could be beta minus 2 alpha also, depending on what the value of Q is, right? But even if Q is 0, this would say that P must be at least 1, because we are saying strictly positive. P must be at least 1, so therefore this thing is 2. On the contrary, if I had taken the other way, suppose this was negative, then this would imply that beta plus alpha is a root, at least. At least this much. This much we can conclude just by looking at the sign. Okay. Yeah. There's another thing we can see, that beta minus 2 alpha beta over alpha alpha, which means which means n alpha beta. Okay, let me write it like this, because this is better to geometrically it's better to write it like this. Alpha alpha alpha. So this is a number. So we are saying this is an integer. So we are saying beta minus this integer times alpha also belongs to delta. This you can see from the so this is nothing else but n alpha beta. So we are saying beta minus n alpha beta alpha also belongs to delta. That's the statement. You can easily see from you can try to take various values of P and Q. You will see that always this guy, this is in the root 6. No? But this has a geometric meaning. You see, this is something that we already observed in the SU3 root case. Right? If you think about it, I mean, if you think in terms of Euclidean plane, right? So I have an alpha here, okay, and beta is something. Let's say beta is something. So look at the plane, a two-dimensional plane in which alpha and beta live. Even in a higher dimensional space, since I'm only talking about these two vectors, alpha and beta, that will define a plane. So in that plane, what is this doing there? So you see, what we are doing with this is, so I mean, if you think about this, this is the dot product of beta with alpha, okay? And then, so this, what this is doing, this is beta, let's say this alpha, and what is that quantity? It is just, you take the perpendicular, plane line perpendicular to alpha, okay, and then reflect it there. So that this guy will be mapped to that. And this one is precisely beta minus 2 alpha beta over alpha alpha alpha. You can see that, I mean, think of alpha maybe not a unit vector, alpha may have some length, no? But what this is doing, I have 2 alpha squared here, alpha length square, there's an alpha here, there's an alpha here. That is the same as taking the unit vector of alpha, right? So, you see what I'm saying? Alpha I can write as, let's say, roughly the length of alpha times the unit vector alpha. This is unit vector, no? So, if you substitute that here, the length all cancels out, and what you're left with is simply unit vector, unit vector. So this takes the projection. So this will take this part, this projection, right? And then reflect it, minus 2. I mean, if it was just minus 1, that would just say that you come back here, right? Because this is the projection. This is the projection of beta along this direction, which means this path. So if you subtract that, then you just come here. But I here minus 2. So you go further there. So that's the reflection, okay? So this is the, of course we knew this had to be the case because as far as the alpha chain is concerned, we have this will form a representation of this SU2, right? And we know that if there is a quantum number m, there should be also minus m. This is what it is. Right? So this reflection is always the case. For every root, you can do that. I mean, you just take the perpendicular plane, let's say, and reflect the whole thing. And the picture will be evaded. The root diagram will go to itself. That's a reflection symmetry. So this much is always there. Now, what is here? Now, the more interesting, okay, this is one thing. This is a geometric picture that we saw already in SU3. But I'm saying that this is now a completely general phenomenon. But the other thing you can do is if you take this n alpha beta and multiply it by n beta alpha. So what's it going to be? It's going to be 2 times 2, 4. B h alpha h beta square, because this is symmetric. B is symmetric. I mean, this is a Cartan-Killing form. This is symmetric in the two. And here you get B h alpha. Well, why do I write? Okay. Since I'm already using that notation, let me just use that. So this is alpha beta square. And here we get alpha and beta. Okay. So you get that. But that is the same. I mean, if you again take the, so this is length square of alpha. That's length square of beta. This is going to be length square of alpha times length square of beta times the angle, cosine of the angle between them, square. No? So therefore, this is nothing else but 4 cos square theta of alpha beta. So this means that it is the angle between the root alpha and root beta. No? So if alpha is here and the beta is there, then this is nothing else but the angle, theta alpha beta. That's what we find here. And this has to be integer, because these guys are integer. So that tells you that the angle theta alpha beta cannot be just arbitrary angle. You see, it must be integer divided by 4. So cos square theta. So anyway, so this has to be integer. So what are the possibilities? You can have theta alpha beta equal to what we are calling 60 degrees. or 120 degrees, right? That's, of course, this will, what is cos of 60? Cos of 60 is 1/2, right? Cos of 60 is 1/2. So cos theta alpha beta is 1/2, or plus or minus half, depending on whatever angles you're looking at. I mean, this or that. So square will be always 1/4, right? For this. What are the other possibilities? I could take theta alpha beta equal to, say, 45 degrees or 135 degrees. So the cos theta for this is 1/√2, right? Cos of 45 is 1/√2. So you get, so cos square theta alpha beta is 1/√2, so 1/2, right? And finally, we can also take theta alpha beta equal to 30 degrees or 150 degrees. So which gives you cos square theta equal to, I think, 3/4, right? Because cos of 30 is √3/2, no? So this becomes cos square theta alpha beta will be 3/4 in this case. But that's it. Because these are the only possibilities. I mean, what we are saying is 4 cos square theta is an integer. This condition tells you is an integer. It is positive, of course, because cos square is positive. So the only possible values are, this could be 0, 1, 2, or 3. 0 I forgot. You can also have theta alpha beta equal to pi/2, 90 degrees. No? That will just make cos theta alpha beta equal to 0. So 0 is allowed, 1, 2, 3. Cannot be anything else because this is going to be, this less than or equal to 1. No? So these are only 4 possibilities. So you see, it's very restrictive. I mean, we are saying that this is extremely restrictive. I mean, all the possibilities are listed in the table, page 95, table 14.1. So the possibilities are all listed in the table, page 95, table 14.1. So all the possible values of n alpha beta are given there, and now let's just try to explain it a little bit. So let's see. Can you raise this now? So let's suppose I take. So let's say I take this 1. So if I can. So cos square theta is 1. So we said there are 2 possibilities. So it's 60 degrees or 120 degrees. But if it is 1, then I mean this has to be also realized as a product of 2 integers, right? I mean this of course this whole thing is an integer, but also I should be able to write it as a product of 2 integers, 2 different integers, because these 2 are not necessarily the same integers. Because this is true with alpha chain through beta, that is beta chain through alpha. So these are a priori different. They are not necessarily equal. No? So if I take cos square theta, 4 cos square theta, alpha beta equal to 1, okay, then that means, of course, the n alpha beta times n beta alpha is equal to 1. Okay, but so what are the possibilities? The only possibility here is that both n alpha beta equal to n beta alpha equal to plus or minus 1, right? That's the only possibility. Now if you take this 4 cos square theta, let me just write down, so is equal to 2, let's say. Which means we are in this case 45 degrees, 135 degrees. Then again, so we have, this should be equal to 1. So I have 2 possibilities, n alpha beta equal to say 1, n beta alpha equal to 2, plus or minus. If this is plus, minus, then it should be also the same sign. If it is a plus, it should be plus, minus, minus. Or other way around. Or I can exchange. N alpha beta equal to plus minus 2 or n beta alpha. You can exchange this. And for the 3, again, the same situation. This will be plus minus 1, and this will be plus minus 3, and again you can exchange. Because these are all prime numbers, no? So there's not, one of them has to be always 1. If it was 4, if 4 was allowed, but 4 is a trivial thing, right? 4 is the same. Because if it is 4, that means cos squared theta alpha beta is 1. That means theta alpha beta is either 0 or 180 degrees. But if it is 0, that means alpha and beta are parallel. So then alpha is equal to beta or minus alpha. No? So these are only 2 possibilities. So it's not 2 different roots. It's either the same root or the minus of the root. So that is a trivial case. So for the 4, if this is equal to 4, then that is trivial. That just means that beta equal to plus or minus alpha. So it's not the two different roots. So this is the picture, and then in the table, then it is summarized how the alpha string proved be a beta, and the length. Yeah, let's look at also the length. That's also another important point. So let us choose. I mean, since there's an exchange symmetry between alpha and beta, here let us make it always that okay. So let's see what does it say here. N alpha beta was this. What is n beta alpha? It's the same as exchange beta and alpha. So it's alpha beta, which is the same as beta alpha. That's the same. But here it becomes beta beta. Right? So if I take the ratio of the two, so if I take the ratio of this, so far we only took the product. But now let's take the ratio of this. When I take the ratio, this alpha beta cancels. Right? But what you get is simply the ratio of the lengths of alpha and beta. So if I take n alpha beta over n beta alpha, this is going to be alpha beta. So it's going to be beta beta divided by alpha alpha. All these factors, 2 cancels, alpha beta cancels, and you just get that. So this is a ratio of n square. So in this table, what one has done is one has always taken alpha square to be the smaller length square in this table. But you could have done other way around, it doesn't matter. But, so in this case, if you take alpha square, so here we just use the notation alpha square, because this is length square. So this is the length, this is length square. Alpha square is the smaller one. I mean, is less than or equal to beta square. We have chosen that. So in this case, so what will happen in this case? In this case, because the two are equal, the n alpha beta, and so both are equal, 1 and 1, both are equal to 1, 1. Okay, this means that alpha square, so beta square equal to alpha square. Correct? Because in this case, both are 1, 1. So this number is equal to that number. So therefore, the only difference between this number and that number is the denominator. So since these are equal, therefore the two length squares are equal from here. In this case, n beta alpha is 2 times n alpha beta. So that is going other way around. So maybe it is taken alpha square. So this is becoming larger. So n alpha beta, so maybe there's a typo in the, no, it's correct. So here, the table is correct. So n alpha beta is greater than or equal to n beta alpha. So here, we are taking always n alpha beta is greater than or equal to n beta alpha. So we are saying then, so this should be really 2 here and 1 there. Okay? And similarly here it will be 3 and 1 in this table. But, okay. So this tells you that beta square is 2 alpha square, and here beta square equal to 3 alpha square. Okay. So that is those are the expressions given in the table. In the SU3 case, we had the angle was 60 degrees or 120 degrees. We never encountered these two cases in the SU3, right? In SU3, this was there. That is why all the roots had same length, right? But there will be more general algebras. We will where you get also this and this. All of these cases will appear. In those cases, the lengths will be different, but in a very specific way. No? So in this case, the length of this guy is square root of 2 times the length of that guy. No? And here it will be square root of 3 times the length of alpha. That's now. So what is that? Okay, so this I will now. Now let me just go to the remaining time. Let me just do this. Just introduce the notion of positive, negative, and negative roots and simple roots, which we discussed already in SU3 case, right? We divided the entire roots into something we call positive and negative. No? And then we also talked about the simple roots. Alpha 1 and alpha 2 are the simple roots. So now we want to give the same definitions now in the more general case. Right? So what is the idea here is, so this is where we need to use is one of the places that we need to use the concept of the regular element. You remember we defined a regular element in the Cartan subalgebra. We said Cartan subalgebra must have at least one regular element, which has minimum number of 0 eigenvalues. So that's where this plays a role. Actually, let me just, before doing that, no, okay, we'll come back to it again anyway. We'll come back to it anyway. Okay, so the regular element, basically a regular element we are saying is something, so there's some regular element, let's call it H naught in H, in the Cartan subalgebra, such that alpha of H naught is not equal to 0 for all alpha belonging to the roots. This is the same definition as the one before, because there we say a minimal number of 0 eigenvalues. Of course, the Cartan subalgebra itself is going to commute with any other Cartan element. So the minimum will be the rank. The minimum 0 eigenvalues will be the rank. Did I define rank? Okay, rank is the dimension of the Cartan subalgebra. Okay. So rank is the rank equal to the dimension of H of the Cartan subalgebra. So, of course, any element by definition, because Cartan subalgebra is the mutually commuting, right? So, every other element of the Cartan subalgebra will have 0 eigenvalue with respect to H naught, including itself, right? So, rank, okay, let me just call this, introduce, I mean, this by this symbol R, okay? So, any H in H will certainly have at least R 0 eigenvalues. Some of them can have more 0 eigenvalues, but minimum they will have this much, right? For example, if you had taken lambda 8 in the going back to SU3 example, so lambda 8 had, of course, 0 eigenvalues was H1 and H2, both of them. But also it had x alpha 1 plus or minus alpha 1 was also commuting with lambda 8, right? So it will have 4 0 eigenvalues, no? 4 independent 0 eigenvalues. So that was not a regular element. So what we are saying, regular element is something which has a minimum number of 0 eigenvalues. And that is exactly this condition. So we are saying that for all the other elements, apart from the Cartan, which are basically given, which are defined by the roots, For none of them, this is 0. Okay? So for none of the non-zero roots, I mean, this eigenvalue with respect to H0 is not 0. So therefore, H0 is a regular element. So that was our old definition, but I'm just rewriting it in a different way. I mean, in a more explicit way. Okay. So if you have that, so we have at least we know that we have such an element. So then I can define positive roots. I can define a concept of positive roots and negative roots. So we define that the positive roots, the set of positive roots, let's say alpha belonging to delta plus. I will now call it, this is the set of positive roots. Our definition of positive roots, this is what we call positive roots, are the ones for which alpha of H0 is positive. Since it is not 0, it can either be positive or negative, right? So we define that. And then negative roots, so this is the positive roots, and negative roots are the opposite sign. Negative roots are the ones for which alpha H0 is less than 0. So those will be the delta minus. So alpha belonging to delta minus. So we split the roots into the positive and negative. I mean, this condition was important because otherwise, if for some alphas it was happened to be 0, then we wouldn't know where to put, whether it should put in the positive or negative. No? But this condition gives a consistent definition. We just split the roots into halves, half of delta plus and half of delta minus. So in particular, if alpha happens to be positive root, we know that for every alpha there is also minus alpha, right? If alpha happens to be the positive root, then minus alpha will be in the negative root, in the negative set. So we will split like that. Okay. Then, now another important definition. The simple root. In the case of SU3, what we said, with our choice of what we meant by positive and negative, we took. So in the SU3 case, just to remind you, we could have chosen this H0 to be. So we could have, for SU3 example, this H0, we were implicitly choosing it to be simply H1 plus H2. H1 plus H2. In that case, so in this picture we had the alpha. In this picture we had alpha 1, alpha 2, and alpha 3. Okay. So this was nothing else but H3 actually. H3 was H1 plus H2. In this SU2 subalgebra, x alpha 3, x minus alpha 3, then the Cartan part which was entering there in the SU2 subalgebra was exactly that, H1 plus H2. Anyway, so there we chose that, and with that choice, you have all of these were positive, and these were negative roots for SU3. And in that case, what we said, so these were 3 positive roots. Yeah, I mean, for example, if I had chosen instead of this, if I had chosen H0 equal to H1, then the plane we'll be talking about will be this plane. And these 3 guys will be positive, this one, and minus alpha 2. This is what will be the positive root with that choice. So which is positive root depends on your choice. But ultimately things will not, I mean, the final results will be the same. That's a matter of your choice. So with this choice we get that. But then we saw that these 3 positive roots, I could write this as a linear combination of these 2, alpha 1 plus alpha 2, right? With the important point being that both the coefficients were non-negative integers, right? I mean, it was plus 1 times alpha 1, plus 1 times alpha 2. Alpha 3 was alpha 1 plus alpha 2. Both these coefficients were positive integers. So non-negative integers, that is. So this was the thing. That is how we defined this. This is what we call simple roots. Right? Because I could always write alpha 3 is alpha 1 plus alpha 2. So it was enough to just focus on alpha 1 and alpha 2, because whatever the action of alpha 3 is, alpha 3 basically is proportional to the commutator of x alpha 1, x alpha 2. And what we were doing is we were defining everything in terms of x alpha 1 and x alpha 2. How we define the highest weight with respect to x alpha 1 and x alpha 2, right? But if there's something which is the highest weight with respect to x alpha 1 and x alpha 2, then it's also highest weight with respect to x alpha 3. No? So we never had to worry about x alpha 3. We could just work with x alpha 1 and x alpha 2. So the similar thing we want to do now in a more general situation. Okay? Completely in an abstract situation. So we do the same thing here. So we say, so the simple roots, okay, so positive root is that, where is the definition of simple root? Yeah. Okay, so what we start doing, let's take alpha belonging to delta plus. Now we are asking the question, if alpha, can we write alpha as some beta plus gamma, where beta and gamma belong to delta plus? So that's the question. If I can write like that, then alpha is not a simple root. So this is the, so if this can be written, if alpha happens to be equal to that, so alpha belongs to delta plus, if alpha can be expressed as a sum of two positive roots, then alpha is not a simple root. So the definition is, the simple roots are the ones, are those positive roots which cannot be expressed as sum of two positive roots. Okay, so this is the idea here. As sum of two positive roots, as sum of two positive roots. So in other words, for no choice of beta and gamma, if alpha is a simple root, then for no choice, alpha cannot be expressed as beta plus gamma for any choice of beta and gamma in delta plus. So those are the simple roots. So which is, in this notes we call the set of simple roots. We always set of all simple roots will denote by sigma. Is denoted by sigma, capital sigma, I think. Yeah, capital sigma. Okay. But now we have to check many things. We have to prove several statements. Maybe I can finish that also. Okay, so another very okay. Yeah. Can I take some more? Because now you see only tomorrow is a day, right? And hopefully at least one lecture in the next week. But even with tomorrow, I'm a bit tired. Just finish this here, right? 14.1, and then we stop. Okay, so again, one of the important property of in SU3, I keep reminding you of SU3 because that you see. So again, we had this picture which was alpha 1, alpha 2, alpha 3. Okay, and so in this thing, we chose this to be positive roots. And then with this definition of simple roots, it's clearly these two are simple roots, right? With that definition, with this choice of positive roots, this was the definition. But now, one important point was that alpha, the difference between these simple roots was not a root. Okay. Because you see, if you take minus alpha 2, it was coming here, minus alpha 2. And now take alpha 1 minus alpha 2, which means this plus that. That is giving you something here, but that was not. Right? It was very important actually, in all these constructions that we did, in constructing the representations and so on and so on. This was an important fact, that neither this was a root, of course this was not a root. So of course this implies alpha 2 minus alpha 1 is also not a root. Now the question is, can we prove in general? Because now we're not working with a specific matrices, no? We don't know anything about it. So can we prove this in general for all these algebras we're talking about? The simple, semi-simple algebras. Is it true or not? So that's the first point. Theorem 14.1. The statement is that if alpha I and alpha j belong to the simple roots here, then alpha I minus alpha j does not belong to simple roots. Okay. So that is it. So let's go through the proof quickly. First of all, okay, alpha I minus alpha j cannot be 0, right? I mean, these are different roots. These are all different roots, simple roots. Okay, so alpha is not equal to alpha j. If it was equal, then of course it will be 0. But I'm talking about two different, where alpha I is not equal to alpha j. So I is not equal to j. So alpha I minus alpha j is not 0. So then there are two possibilities then. Since it is not 0, since alpha I minus alpha j is not equal to 0, there are two possibilities. Either it is a positive root or it is a negative root, right? Because we said all the roots have been split halfway, half, positive and negative. So there are two possibilities. Either alpha I minus, so two possibilities here, is a positive root, so belongs to delta plus, which means it is equal to some, let's say, beta, which belongs to delta plus. Okay. But that is impossible, because this would imply that alpha I equal to alpha j plus beta. Right? But our definition was, and both are positive roots. Alpha j is a positive root, this is a positive root. Okay? But under this assumption. So, but then this could not have been a simple root, because by definition a simple root could not be expressed as a sum of two positive roots. So this is not possible. What about if suppose it was a negative root? So suppose alpha I minus alpha j is a negative root, belongs to delta minus. That means it's equal to some minus beta for some beta in the positive root, for some positive, so beta in the delta plus. Right? Again, I'm using the fact that for every root there's a negative of the root. So this is the second possibility here. But then I can write alpha, you can move this beta there and alpha j there, then this would imply that alpha j equal to alpha I plus beta. And these two are positive roots, so it's again a contradiction. So this is a very general fact, I mean, general statement. It's not just something exceptional for SU3. This is general. Okay. The second point is alpha I dot alpha j is always negative. I mean, less than or equal to 0. So alpha I, alpha j. So if alpha I, alpha j belong to sigma, okay, with I not equal to j, alpha I, alpha j is always less than or equal to 0. Okay. And the statement is okay. So suppose, so again assume the contrary, assume the opposite, assume the contrary. That is alpha I, alpha j is positive, is greater than, strictly greater than 0. But then we already know this formula that 2 alpha I, alpha j divided by alpha I, the chain, alpha I string through alpha j. This is going to be equal to P minus Q. Okay. So remember, so this was the chain. We started with alpha j here, alpha j plus alpha I, all the way up to alpha j plus Q alpha I, and here alpha j minus alpha I, all the way up to alpha j minus P alpha I. So this was the chain. This was the string, alpha j, alpha I string. Now, if this is, I mean, this is certainly positive. We already know this positive definite, this space, right? So this is positive. And we are saying that if this is also positive, okay, then the left-hand side is positive. That means P must be certainly greater than 0, right? I mean, so suppose this was plus 1, okay? Then P must be equal to Q plus 1. Okay, but Q is at least, I mean, Q is greater than or equal to 0. So the minimum value of Q is 0. So P would be 1 in that. If this was 1, P would be 1. So the upshot is that no matter what the value of Q is, P certainly is a positive number. Positive, strictly positive number. So in particular, P equal to 1 is also allowed, right? Whatever the value of P is the first step is actually alpha j minus alpha I. But we have already proven before that alpha j minus alpha I is not a root. No? So P has to be 0 actually, because this root is not existing. So P has to be 0. No? That's not possible. So therefore this is not possible. So that's so always, of course, here you see that this angle is 120 degrees, right? So cosine of 120 is negative. So this was a minus. Dot product was minus. Okay. Finally, now I will present this third and fourth proof in a different way. Yeah, I will. Yeah. What I will do is I will first prove the 4 and the number 4, which is, because then number 3 is obvious, we don't have to prove. Number 4, if you prove number 4, number 3 is already proven. So number 4 is that if alpha belongs to delta plus, then alpha is a linear combination of simple roots. Simple roots with positive coefficients. Okay, with non-negative coefficients. Basically. And the way to prove it is, so basically the idea is very simple actually. So I mean, so if alpha itself, if alpha is not sigma, not in sigma, okay, then by definition alpha can be written as some beta plus gamma, where both are in the positive, both beta and gamma are positive roots. Both beta and gamma belong to positive roots, delta plus. Okay. Then you ask the question. Okay, so I express. So suppose it's not. If alpha was already in the simple roots, then I have to prove nothing, right? Basically, what we are saying is that every positive root can be expressed as a linear combination. So if alpha is not in sigma, then I can write like this. Now, the two possibilities. Maybe both of them are simple roots already, or maybe only one of them is a simple root and the other is not a simple root but a positive root. Huh? So suppose both of them are not. simple roots. Then I can write this again as combinations of some, I don't know, beta 1 plus beta 2, and this guy gamma 1 plus gamma 2, and so on. You can keep going with steps. Then again you ask the question, are they simple roots or not? If they're not simple roots, again keep going down. Okay. At some point you will end up with hitting the simple roots, because it's all finite dimensions. Number of roots is finite. No? You keep going. So at the end, after several steps, you will end up just writing it as a linear combination of the simple roots. Okay. So after some finite number of steps, because we are all talking, after a finite number of steps, okay, then alpha can be written as some linear combination of simple roots with non-negative coefficients. Non-negative, so some ni. These are all integers, and I mean non-negative integers. This you can do. And once you have done that, once you accept this 4, then 3 is automatic. The 3 was that this alpha I, the sigma, provides a basis. Provides a basis for H star as a vector space. That is the reason was because we already have seen that we have already gone through a theorem that alphas span the vector space. All the roots span the vector space, right? Which means in particular the positive roots span the vector space, because negative root is simply minus of the positive root, right? So it spans the vector space, and since I can obtain all the alphas, all the positive roots as actually, in fact, what this argument shows is that not just that any positive root can be expressed, any positive root can be written as a linear combination of the base thing, but also negative roots, because negative root is some minus of alpha, no? Where alpha is a positive root. So if I can write alpha as a linear combination of non-negative integers of simple roots, then the negative roots will be linear combination of simple roots with a non-positive coefficients, because you just have to take the minus of the whole thing. Okay. So basically all the roots can be expressed as linear combination of simple roots, either with non-negative coefficients or non-positive, or all non-positive coefficients. No. So therefore, since we know that all the alphas span the entire H star, and since every alpha can be expressed as linear combination of the simple roots, so simple roots provide a basis. Right? And this also then proves that the number of simple roots is exactly equal to the dimension of the Cartan subalgebra, which is a rank. Okay. So sigma, so the number of elements in sigma is equal to the rank, which we are denoting by R. The rank of the dimension of the Cartan subalgebra. Since it's spanning R dimensional vector space, it's providing a basis, so it must be R. That's the statement. So this is, I think, it stops here. No, yeah. So right. I think that tomorrow I will continue with this, and we'll arrive at a complete classification of simple real algebras. Complete classification. Using this now. I think some of the things I'm not going to give proofs, but at least try to motivate you why that seems reasonable, the statements. But essentially, it's from here. I mean, we will start getting into this. And then probably I will try to also, construct all the rank 2 algebras. Rank 2, SU3 was an example that we have done. Rank 2 Cartan subspace 2-dimensional. Other one is SO4, and then SO5. Both of them are rank 2. Well, SP1, SP2, rank 2. SP2, yeah, it turns out is equal to same as SO5. But then in that process, we will find a completely new algebra, which was not one of the things which we knew from the matrices. No? From matrix algebras, the only thing we know is SU series, SO series, and SP series, subtracted. No? But we'll find a totally new algebra just from this classification, which is called G2 algebra. G2 algebra, G2. This has played a very important role in the recent times in so-called M theory, master theory, or the mother theory, they call it, I don't know what that M stands for. You know, because the people who initiated the symbol M, they never explained what was their motivation, why they called it M. But anyway, it's supposed to be a theory which includes everything, all the string theory and everything. So that's why it's called master theory, you know, from where everything originated, or mother theory. But anyway, so the G2 plays an important role. So, but it was quite interesting that, you know, that with this classification they found that essentially what we knew, the matrix algebras, they are essentially everything except for a few handful of them. G2 is one of them. There are some other, something like another 4 more such unconventional algebras which are not discovered from matrices, which was completely new, which came from this classification. And new meaning, it's old, but it was discovered a long time back. Not new in the sense of. Okay, so I will meet tomorrow and continue with this. And then if I get some time, I will try to go back and go to that chapter 14 which I skipped. No? But I don't think I'll get time though. Okay, so any questions here? Okay, so then I will see you tomorrow.